Hi, in this lecture I want to talk about a very simple model known as the binary random walk model. Now, binary random walk model works as follows. Assume that each period I flip a coin, and it can either come up heads or come up tails. All I want to do is turn that idea into a model. Here's how I'm going to do it. I'm going to define a variable called x, and that's going to be my winnings. And then I'm going to have a fair coin, and if I flip it, if it comes up heads half the time, then I win $1. And if it comes up tails, then I lose $1. And then what I'm going to do is I'm just going to keep track of how much money I've won. So if it turns out I win the first time, this goes to 1. If I win again, it goes to 2. Then if I lose, it falls back down to 1. That's all there is to the process. Now, you can think of this as a decent model of gambling, so going to a casino and playing blackjack. Maybe there's a 50% chance you win a hand, 50% chance you lose a hand. Suppose you bet $1 on each hand. The random walk describes what your winnings would look like. And here's sort of a picture of what that would be. You might win the first hand and then lose and then lose and then lose and then win and then lose a couple and then win, and you'd be down, let's say, $2 in this case. This is what we mean by a binary random walk. What I want to do is I want to start out with 3 mathematical results about these binary random walks that are sort of surprising. First one is this. If you play this n times, 100 times, 1,000 times, 1,000,000 times for any n, your expected winnings are going to be 0 because it's equally likely to go up or down. So that one makes a lot of sense, right? Half the time you go up, half the time you go down, you should expect to break even. Now some surprising results. Result 2. Pick any number k, 10, 50, 500. If you have a random walk that goes on forever, you're going to pass plus k and minus k an infinite number of times. So what that means is if here's 0, and here's plus 500, and here's minus 500, your random walk is going to cross each one of these an infinite number of times. What that means is it's not going to take off. There's no way it's just going to take off where you win billions and billions of dollars and never go negative. So if you're playing blackjack and you played forever, if you went to a casino and played blackjack forever, it's an infinite number of times you're going to be up $500, an infinite number of times you're going to be down $500. That's just a mathematical fact. Now here's the third mathematical fact that may be even more surprising. Again, if you play long enough, you're going to get a streak of k heads in a row and k tails in a row for any k. So let's take k equals 30. If you sit down at a blackjack table and played hand after hand after hand for decades, you'd win 30 times in a row an infinite number of times. You'd also lose 30 times in a row, eventually an infinite number of times. So if you see a streak, we often think, oh boy, that streak, I was really hot, I was really winning, the cards are falling my way. No, it's just going to happen. It's going to happen because that's what the math tells us. Now let's see how the math explains that. What are the odds that you win once? A half. What are the odds that you win twice in a row? Well, 1/2 times 1/2 because you've got to get 2 heads in a row. What are the odds you win 16 times in a row? Well, that's just a half times a half times a half times a half, 16 times, which is 1/2 to the 16th. Well, how big of a number is that? That's around 64,000. So the odds of getting that are actually 1 in 64,532. So you think that's not that likely. But here's the point. Suppose there's 100,000 people sitting at casinos. If there's 100,000 people sitting at casinos playing blackjack, you'd expect one of them to get even more than 1, maybe 1.5, to get 16 wins in a row. And those people are going to fly back home and they're going to say, oh man, I was so lucky. No, they just happened to have that one random walk that had 16 heads in a row. There's probably someone else that went home losing 16 times in a row. They probably took the bus. So what you get is, with a random walk, you're likely to get these long sequences. You're also going to end up at 0, and you're going to pass above lines, and you're going to fall below lines. There's going to be big winners, big losers, and it's just random. Now there's another phenomenon, what that means that's implicit in those results, and that's regression to the mean. So the first result said you're going to expect to be at 0. The second result said you're going to be above 500 an infinite number of times and below negative 500 an infinite number of times. Another way to think about that is if you have a random walk, it's just going to, on average, go back to 0. So if you think about, suppose I'm up 50. Well, if I think what's going to happen in the next 20 periods, I should expect to be right back at 50. I shouldn't expect to keep winning even though I've won before because there's no bias upward. So if you think about things like free throw shooting, these are examples where we think like, oh man, people get hot. So there's a famous study called the hot hand study, and they looked at the 1980-81 Boston Celtics. And now instead of thinking of a random walk where it's 50% likely to go up and 50% likely to go down. Here, the Celtics made 75% of the free throws. So it's 75% chance it's going to go up and a 25% chance, in some sense, you can think of the walk going down. So if people really did get hot, if there really were hot hands, you'd expect it to be the case that after you miss a free throw, you're less likely to make it than after you made a free throw. Well, they looked at an entire season worth of data, and they found that if you miss your first free throw, you make the second one 75% of the time. But if you make your first free throw, so you're feeling it, then you make the second free throw 75% of the time. So here's the point. We may think there's all sorts of hot streaks out there and hot hands and things like that. If you actually look at the data, many of them turn out to be just simple random walks. Now, the probabilities aren't always 50%. In this case, they're 75%. But again, this process, the free throw shooting of the Boston Celtics in 1980, was just a straightforward binary random walk with the probability going up 1.75, the probability going down 1.25. This doesn't stop us, though, whenever we see streaks to think, oh boy, this person must have really some great skill, or they must be hot, or things must be going that way. But this is a problem, because if you try and infer from someone's success that what they're doing made them successful, that can be wrong. It could be that you just happen to be seeing a sequence of 16 heads in a row. So there's a famous book written by Jim Collins called Good to Great. And what he did is he looked at a whole bunch of companies that have been successful, and then he said, let's see what the characteristics of those companies are. And what he found is these are the companies that are good to great. These are what they have. They have humble leaders. They have the right people on the bus. They have the right employees. Not necessarily the smartest employees, but the right employees. They confront facts. They don't delude themselves. They look out there and they say, this is a fact. This is where the market's moving. This is what our competitors doing. They don't delude themselves in any way. They focus. They focus on whatever it is that they're trying to do. They also rinse their cottage cheese. What does this mean? This refers to a triathlete named Dave Scott who trained like an unbelievable amount of time. He ran and swam so much every day it would just blow your mind. And yet this same guy rinsed his cottage cheese so that he wouldn't have too much fat in his diet. So it's this total commitment to what you're doing. They also embraced technology. So they were people who weren't afraid of technology, and they sought out what we called super additivity, this idea that you get one good idea in one place and another good idea in another place, you could combine them. So these were the characteristics of companies that were good to great, and this was the best-selling business book of all time. Now here's the list of the great companies in 2001. Places like Abbott Laboratories, Circuit City, Kroger, Philip Morris, Pitney Bowes. We can then ask, how did those companies do over the next decade? And here's the answer. Not very well. So the S&P 500 went up 0% during that time. The ones in red are the companies that didn't do very well. So only two companies went well. Gillette, which was bought by P&G, and Nucor, which stock went up fourfold. But many others didn't do well at all, including Fannie Mae, which went into receivership. So not explicitly criticizing Collins, what I'm saying is that if you have success in the past, a lot of that could just be that things fell your way. That maybe it was a complex process and luck went your way and your coin came up heads 10 periods in a row. And what you often get is regression to the mean. And so what we see here in these great companies is just standard regression to the mean. Now some of you may be thinking at this point, wait a minute, this seems like one of our earlier models, and it should. Remember the no free lunch theorem? The no free lunch theorem said no algorithm is better than any other. So big rocks first, little rocks first, it depends on the context. Well, that same thing may be true here. So if we go back and look at what Collins identified, humble leaders, right people on the bus, technology, super additivity, it may well be that these were all really good heuristics for the time, for the period from 1990 to 2001, and hence he's able to identify these companies that were great, they're the ones that really ascribed to those particular techniques. However, from 2001 to 2010, those same heuristics may not have worked very well, and so we know from the no free lunch theorem that any heuristic, humble leaders, rinsing your cottage cheese, whatever it is, may work in one setting, may not work in another setting. And so it could be, if it's luck, whether your particular heuristic is working at any given moment in time, you'd expect to see this sort of regression to the mean. There's a related idea to this notion of sort of streaks, and that's clusters. Now you've probably noticed, if you look on the internet, there's all sorts of spatial graphs. So we can see all sorts of graphs where things are situated in space. So you might see data that looks like this. Now when we see data that looks like this, we might say, oh boy, it looks like there's a cluster here, and a cluster here, and a cluster here. And if this were, let's say, data on cancer or crime or something like that, you might think, boy, we better go and identify what's going on in that cluster. Well, here's the problem. If I just randomly throw things down on a graph, I'm going to get clusters. Let's suppose I have a 1,000 by 1,000 checkerboard, and I fill in each square with probably 1/10. So I fill in 100,000 squares. This is 1,000,000 squares, I'm filling in 1/10 of them. And I want to ask, how many clusters are there that are this big, that are 5 by 5? Well, there's 996 times 996 clusters that size. So the point is, there's just going to be a whole bunch of places where I might have a lot of these dots filled in. And then I might think, oh my gosh, that square right there, that square, something horrible's happening. Or if I want to ask, how many rows of 10 are there? Well, there's 990 times 1,000 rows of 10. So it's going to be very likely, just like it's likely that someone throws 16 heads in a row, that I'm going to see some strip of length 10 where a whole bunch of them are filled in. And then I'm going to think, wow, something must have happened here. But the reality is, something necessarily didn't happen there. It could just be that it's random. So when you look at graphs and you see these clusters, you have to be aware that they may just be random, just like when you see somebody win 15 times at blackjack, or when you see some company be incredibly successful. So what have we learned? What we've learned is we can often think of an outcome as being a sequence of random events. And if an outcome is a sequence of random events, what we're going to expect to see is we're going to expect to see an expected value of 0, but we're going to see some big winners and some big losers. And we can't then necessarily infer, just because someone's been successful in the past, that they're going to be successful in the future. So if we start with 2 random walkers, and one who happened to go up and one who happened to goes down, and then we think right here and say, who are we going to place our bets on? Well, this one's just as likely to go down as this one is to go up. We don't know anything. So what we really want to try and figure out in these situations is something a random walk, or is it not? Is there some reason to believe that this person's going up for a reason, and this person's going down for a reason? Or is the data consistent with things being purely random? And if it is, we should expect some regression to the mean. We should expect the two of them to perform about the same. All right, thank you.